Alright guys, in this one we're going to talk about the ratio test, and it's going to be the last test for convergence that we're going to talk about. It's pretty straightforward. It says let the series have non-zero terms, so there's nothing going to be zero, they're all numbers. So it says the series converges if the limit of the a sub n plus 1 term over the a sub n term is less than 1. So what this is, like, let's think of that like the current term. A sub n is the term right before it, the previous term. Or if a sub n is the current term, a sub n plus 1 would be the next term. If I had a sequence a sub 1, a sub 2, a sub 3, this is a sub n, this would be a sub n plus 1, this would be a sub n plus 2 if we said n was equal to 1. So it's the limit as n goes to infinity of the next term over the current term. And if that's less than 1 in absolute value, then that series is going to converge. It's very similar to a geometric series where this is like our number, our R number. If it's less than 1, it's going to converge. If it's greater than 1 or it's infinity, it's going to diverge. If that limit diverges, meaning the terms are getting bigger and bigger. So if I had like the first term was 2, the next term was 4, the next term was 8, I don't know. If I divided the next term over the current term, each time that R number is like 2 because they're doubling, so that thing's going to diverge. It's going to keep growing and growing and growing. But if it's the other way around, 8 to 4 to 2, if I do the a sub n plus 1 over the a sub n term, 4 over 8, and I'm looking at that limit, if that number is less than 1, in absolute value, so don't look at the negatives, if it's less than 1, then that thing's going to converge. Very similar to the geometric series rules. And that's kind of how I think of these, is kind of like geometric series. So the ratio test is inconclusive if that limit is equal to 1. All right, so let's do a couple examples and see what all could happen. In this first one, determine the convergence or divergence in the following series, and it says use the ratio test, so it's kind of nice. So what I'm going to do is I'm going to say it's the limit as n goes to infinity of the a sub n plus 1 term, so plug in n plus 1 for both of the n numbers, divide it by the current term or the original. So that is just going to go on the bottom. And if I plug in n plus 1 for n's, that's what goes on top. So there's your a sub n plus 1 term. That's what this is. This is the a sub n plus 1. And this is the a sub n. So there's that look to it. All right, now I'm going to evaluate this limit. So I'm going to say this is equal to the limit as n goes to infinity. I'm going to keep the top part, and I'm also going to go ahead and rewrite it. So a to the 2 to the n plus 1 would be 2 to the n times 2 over n plus 1 times n factorial. I'm going to keep change multiplication and then flip the second fraction. And that'd be 8 to the n. So you're going to see why I went ahead and rewrote this as 2 to the n times 2, because that cancels. And factorials cancel, and I get this is equal to the limit as n goes to infinity of 2 over n plus 1. And now I got to evaluate that limit. Okay, this limit as n goes to infinity is 0, which is less than 1. So therefore, the series is going to converge by the ratio test, or using the ratio test. All right, easy peasy. All right, let's do another one. All right, so it's going to say use the ratio test. We know it's going to use the ratio test. When to use it is going to be the harder part. If we mix them all up, knowing which test to use is going to be the tricky part. But never mind. We'll do that later. All right, so I'm going to find the limit as n goes to infinity of the n plus 1 term. This would be n plus 1, but it'd be plus 1 plus 1, so it'd be plus 2, over 3 to the n plus 1, all over just the original n squared to the n plus 1 over 3 to the n. And I gotta think, what is this limit? So I'm gonna rewrite this as the limit as n goes to infinity. The top part, I might not need to expand that. Not sure yet. Maybe we'll just expand it, see what happens. It'd be m squared plus 2n plus 2. I'm going to rewrite this as 2 to the n. So since it's the n plus 1 on the bottom, I'm going to write n plus 1 times 2 like that. So this is equal to 2 to the n plus 2. I'm trying to rewrite it and make it look like the bottom. 3 to the n times 3 times, flip that bottom one, n squared 2 to the n plus 1. All right, and now I'm going to cancel out the things that are the same on top and bottom. So it looks like on the top, I'm just going to rewrite this as equal to the limit as n goes to infinity of 2n squared plus 2n plus 2 over 3n squared. And I know as n goes to infinity, this limit would be 2/3, which is less than 1. And I should have written this on this paper, on this problem. Less than 1, therefore ratio test. All right, so since that's less than 1, therefore the series converges by the ratio test. All right, so the tricks are going to be kind of seeing how to rewrite these terms, the ones with the n plus 1s, as things that will match what's on the bottom so they cancel out. That's going to be the trick that just takes time. All right, so it says use the ratio test. So I'm going to say, okay, well, this is the limit as n goes to infinity of n plus 1. Wherever there's an n, I'm going to plug in n plus 1 over n plus 1 factorial over n to the power of n over n factorial. This will be equal to the limit as n goes to infinity. And I'm going to go ahead and start trying to rewrite this to match something that looks like on the bottom. Might not be perfect here, but let's just try something. We'll say this is n plus 1 to the n times n plus 1. It's not going to be perfect, but we'll just see what happens. Over n plus 1 times n factorial. That was rewriting this one. So knowing 4 times 3 times 2 times 1, that's a 1. That's what 4 factorial is. So if I said n plus 1 factorial, that's going to be n plus 1 times n minus 1 all the way down to where it just gives you 1, right? So if n was 5, I plug in 5. So it'd be 6 factorial would be equal to 6 times 5 times 4 times 3, on and on and on and on and on. Or another way to write that would just be equal to n plus 1 times n factorial, because this would be n factorial if it continued on. All right, times n factorial over n to the power of n. That's what the bottom was. All right, and now we got to start seeing what can we cancel out. The n factorials cancel out, the n plus 1s cancel out, and I'm left with this limit as n goes to infinity of n plus 1 to the power of n over n to the power of n. And I notice that this is the same exponent, so I'm going to rewrite that as the limit as n goes to infinity. And this would be n plus 1 over n to the power of n. And this is a tricky one, kind of bad. To equal the limit as n goes to infinity of 1 plus 1 over n, if I divide each term by n, to the power of n, which is the number e. Isn't that clever? All right, so this is kind of a special one. Hopefully you remember back from your Algebra 2 days that this limit, e is defined to be this limit. It's a special limit. It's just, if you didn't see that, it's kind of hard to see it, but that's kind of fun. All right, therefore, the series diverges by the ratio test, because the limit of the next term over the term before it is going to approach the number e, which is greater than 1, so diverges. All right, last one of this part, and then we'll kind of talk about all the different things, all the different series, and just kind of recap it. All right, so this one looks like an alternating series. It's an alternating series. So I'm going to ignore that because in the ratio test, it just looks at, excuse me, the absolute value. So it being positive, negative, doesn't really matter. So I'm going to ignore it while I look at the limit. The limit as n goes to infinity of the n plus 1 term, that'd be like n plus 1, so n plus 2, over the square root of n over n plus 1. I'm going to evaluate this limit. I just took away I took the absolute value, so I'm not looking at the negative. That's going to be equal to, and I can go ahead and write this if I wanted to. I'm not going to. Okay. The limit as n goes to infinity of n plus 1 over, I'm not going to break anything down. Let's just see what happens. Oops. Times n plus 1 over the square root of n. As n goes to infinity, does adding 1 really affect anything? Does adding 2 really affect anything? I'm trying to give you a good reason why this is equal to 1, but I'm kind of blanking. As n goes to infinity, this is basically, oops, I'll undo that. As n goes to infinity, adding 1 doesn't change it. It's basically that. As n goes to infinity, adding 2 is basically adding 1. It doesn't affect. So the limit is just going to be 1. And when that happens, the ratio test is inconclusive. All right, so that's it for this video. Hopefully it gives you an idea how the ratio test, to me, kind of looks like the geometric series test. I look at the limit as one term over the term before it, what that's doing as n goes to infinity. And if that number is less than 1, the series converges. If it's greater than 1 or infinity, it diverges. If it's equal to 1, like this one was, it is inconclusive. We got to try other things. So thanks for watching this video. If you have any questions, next time I see you in class, bye. Next time I see you in class, ask. Bye.